Well, hello and welcome again to Maths 315, Analysis and Topology. This is the third recording for Chapter 1. And we've been looking at some limits to infinity, and we looked at lots of examples of dealing with rational functions and taking limits of rational functions. And I was going to look at a slightly more difficult example here. And this one here is we're going to look at the limit as x becomes very large of the square root of 2x plus 3 minus the square root of 2x. Now this is not of the same sort as we've had before, although we'll see we can get to such a thing. One is tempted, and please do resist temptation, to say things like, well, as x goes to infinity, this is infinity minus infinity, and that's equal to something. Well, it doesn't. Infinity, I can make infinity minus infinity into any number I like, in fact. Now it turns out the answer to this limit, as we'll see, is 0, but it is not infinity minus infinity. You cannot just plug infinity into things and hope that something sensible will happen. So do beware of that. You treat infinity with great respect because it's a very tricky concept. So how are we going to deal with this limit then? Well, here is the solution to this. And what I'm going to do is I'm going to use our old idea of the difference of two squares. So I've got a difference of two square roots here, and I really want to get rid of these square roots, at least in the numerator. So what I'm going to do is I'm going to multiply this thing by its conjugate. That is, I'm going to copy the same thing down. I'm going to put a plus in the middle. And here I'm exploiting now difference of two squares, that if you've got a minus b times a plus b, you get the first squared minus the second squared. And that'll get rid of the square roots for me. Now whatever I do to the top, I must do the same to the bottom. So at school you learned about rationalising denominators with these surds, and here we're going to rationalise the numerator. So I multiply this minus this times that plus that one. And so by our difference of two squares formula, we get the square of the first minus the square of the second. So that gives me 2x plus 3 minus 2x. In the denominator, I've got root 2x plus 3 and plus 2x that we had from here, because whatever you do to the top of a fraction, you must do the same to the bottom. Well, something nice happens now. The 2x's cancel, and I just get 3 over this quantity. And now I can use my intuition and say, well, if x becomes very large, this is becoming very large, so is this. There's a plus in the middle. Large plus large is large, and 3 over large in the limit goes to 0. Now you'll see another example in the tutorial problems, a similar one, where in fact you don't get the limit 0, even though it looks not quite that much different to this one. You have to do this sort of calculation each time to work out what the exact limit is going to be. So that's a little bit on limits to infinity involving rational functions. And now I'm going to have a look at what happens if we introduce some trigonometric functions into the story. So recall that the trigonometric functions, sin x and cos x, they're bounded between minus 1 and 1. Sin and cos can't be bigger than 1, and it can't be less than minus 1. They're trapped in that region. That means then, if x is very large, the function sin x over x will again become very small, because sin x can't be very big. If someone offers me sin of $1 million, I tell them to keep it because it's worth nothing. Sin of 1,000,000 is just some funny number, but it's between minus 1 and 1. It's not worth very much. So the sign is bounded, but the x on the bottom is becoming very large, and so this quantity again is going to go to 0. It's going to become very small as x becomes very large. Now again, we'll prove this in more detail later, but for the present we're just going to accept it as a fairly obvious fact. So we're going to have a look at the limit as x becomes very large, of 2x plus sin x on x minus cos x. So here is the worked part of this, the solution to this problem. Here is our limit. X becomes very large. We've got 2x plus sine x, x minus cos x. And again, you ask, where's the money? Sine of $1 million, keep it. It's not worth very much. Cos of $1 million, not interested. That's where the money is. There's 2 million up here and 1 million down here. So they're the dominant terms. And once again, we're going to divide by the highest power of x in the denominator. So I divide everything here now by x. So I'm going to divide by x. So 2x on x is 2, sine x on x, 1 minus cos x on x. And now we're simply going to say that as x becomes very big, sine and cos are bounded. So this is becoming very small, this is becoming very small, and I just get 2 over 1, which is 2, because sine x on x and cos x on x go to 0 as x goes to infinity. So that's a little example there involving some trig functions. Now the next little bit we're going to have a look at in terms of our limits, and again we will come back and do this more formally in a later chapter, but as well as looking at limits to infinity, one can also be asked to find limits at a point at which a given function may not be defined. It may not even exist at that point, but one can look at limits. For example, if I take the function f of x as x minus 1 on x squared minus 1, you can't put x equals 1 in. You get 0 over 0. Now 0 over 0 is undefined. It doesn't have any meaning in mathematics. Some people think 0 over 0 is 1 or something. This is nonsense. 0 over 0 doesn't mean anything. It's undefined. It's a bit like 0 to the power 0. It doesn't mean anything. It's undefined. However, if I type this into a graphical calculator or computer and ask it to draw the picture of this, then I'd find that as I look near 1, not at 1, but near 1, the function would appear to be approaching some finite number as x gets close to 1. And we'd like to know what that is. So again, in terms of notation, we're going to be looking at the limit as x approaches 1 is the way we're going to read this. It's not x equals 1. You cannot put 1 into here. It doesn't make sense. But you can say what's happening to this expression as x gets as close as we like to 1. And so I'll work through this one, and then we'll have a look at a couple of other examples of these finite limits. Okay, so there it is, limit x goes to 1, x minus 1 on x squared minus 1. And you look at the denominator here, and I hope immediately, as soon as you see x squared minus 1, you are tempted to factorise this using the difference of two squares. That would be a very natural thing to do. So I factorise x squared minus 1 into x minus 1 on x plus 1. Now x at the moment is not 1. X is approaching 1, but it's not 1. So I can cancel these terms out. These are not 0 because x is not 1. So I can cancel these terms out, and I just get 1 on x plus 1. And now I ask the question, well, as x gets close to 1, what's 1 on 1 plus x doing? Well, obviously it's getting close to 1 plus 1 on 1, which is 2. And so we say the value of this limit is 2. It doesn't mean that this thing here equals a half. It doesn't mean that this thing equals a half when x is 1. It simply says this is getting close to a half as x gets close to 1. That's a very important meaning. Okay, so that's our little first example there of one of these, and I like to do a couple of examples, so I'm going to do another one here, slightly more complicated. We're going to look at the limit. Now as x gets close to 2 of x squared plus x minus 6 over x squared minus 4. Now what happens if we were to just plug in 2? Well, I'd get 2 squared is 4, plus 2 is 6, minus 6, the top is 0, and you put 2 in the bottom, you get 2 squared minus 4, well that's 0, and so once again we're getting 0 over 0. Well, we're not allowed to have that in mathematics, so you can't just whack You can't just whack x as 2 in and hope for the best. It doesn't work. So I'm going to do, here's the solution of this, correct solution of this limit. We're going to do much as we did last time. I've got a quadratic on the top, and so when you see a quadratic, first thing you often think of is, can I factorise the quadratic? And the answer is yes. It factors to x minus 2 on x plus 3 over x minus 2x plus 2. I can factorise that again as a difference of 2 squares. Now again, if x is not equal to 2, then I can cancel, so this is not 0, I can cancel these terms out. So I just get x plus 3 on x plus 2. Now I can say, well, if x is very close to 2, then x plus 3 is getting very close to 5, and 2 plus 2 is getting very, or x plus 2 is getting very close to 4, and so the limit is going to be 5/4. And that's the value of the limit of this function here. In other words, this expression is getting closer and closer to 5/4 the closer x gets to 2. Well, we'll leave limits for the moment, and we're going to talk a little bit about sequences. And again, we're going to come back and look at these in far more detail in the next chapter, where we'll look at what we mean by limits of sequences more formally. But here, you've already come across the notion of a sequence. I just remind you, it's simply a function from n, the set of natural numbers, that's numbers 1, 2, 3, and so on, to the set of real numbers, which we call R. So it's just a formula. You plug in whole numbers, one after the other, and you get some real number pops out. Now, instead of using function notation x of n, we're going to use subscripts, and we're going to write x sub n for the sequences. Now, sometimes we will start our sequence at n equals 0, which you might say, well, hang on, the n equals 0 is not technically a natural number. Some people, in fact, I think I generally do, start the natural numbers at 0. Some people start them at 1. So anyway, sometimes we'll start with n equals 0, and sometimes we'll start with n equals 1, or perhaps some other number, whatever we care to do. So here's some examples of these. So we've got 1, 2, 4, 8, and I really don't like writing sequences like this, because you might, if I asked you what do you think the next number might be, well, you'd probably say 16, you're doubling all the time, 2, 4, 8, 16, 32, and so on. However, you have to assume that that is the pattern. You have to assume that is the pattern. I mean, I could have been adding on 1, 2, and then add on 4, and then I could add on something different and get another number here. But anyway, that's an example of a sequence where if the obvious pattern continues, you'd expect the next number to be 16. Here's another sequence, 2, 5, 8, 11, 14, and again you might guess the pattern here, if there is one, is that you add 3 onto each term, so you might think the next term is 17, 20, and so on. Here's a very famous sequence, the 1, 1, 2, 3, 5, 8, 13, 21. This is meant to be the so-called Fibonacci sequence, where every number, once we get past the first 2, every number is the sum of the 2 before it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. So the next number would be 34, and then 55, and then 80 something, 89 I think, and then 144. I'll leave you to write some more of these out. By the way, 144 is the only square Fibonacci number, apart from 1. If you write these out, you'll get it to eventually 144. It turns out to be the only square Fibonacci number. And the numbers could go into fractions, so we could have 2, 1, half, a quarter. Here I'm dividing by 2. Now, as I said, I don't like writing sequences like this because we have to assume that there's some sort of pattern and that I'm clever enough to work it out. So in the above, the sequence is simply given as a list, and one tries to look for a pattern which may or may not be there in the first place. For example, if I give you this sequence, 1, 2, 5, 14, 42, what's the next number? I've got no idea. I can't even see what the pattern might be here. I could put any number down next to that one. So it's not obvious as to what the pattern is in this sequence. I'm sure I could cook up something where this would follow some kind of pattern, but it's not obvious what it is. So it is much better, that's a T there, so it is much better to describe a sequence by a formula which makes explicit what the pattern is. So it's much better to describe a sequence by a formula. So for example, here is a sequence. Xn is a half n, n minus 1, for n equals 1, 2, 3, and so on. So you put n as 1 in, well 1 minus 1 is 0, so the first term in the sequence is 0. You put n as 2 in, you get 2 times, so you get 2 times 1 divided by 2 is 1. Put n equals 3 in, you get 3 2s, so 6 divided by 2 is 3, and so on. And you get these numbers 0, 1, 3, 6, 10, and so on. And these are called the triangular numbers. And you might like to Google triangular numbers, and you'll get lots of useful, interesting information. They've got lovely, lovely properties. But they don't concern us here, they're just an example. Some sequences alternate in sign. For example, this sequence a sub n is, I'm going to write as minus 1 to the n times 1 over n. And this minus 1 to the n, well, if n is an even number, then this will be minus 1 to an even number is 1. And if n is odd, minus 1 to an odd number is minus 1. So if I put n as 1 in, then I'm going to get minus 1 times 1 over 1, that's minus 1. You put n as 2 in, n is even, so that's positive, I just get a half. You put n as 3, you get minus a third, plus a quarter, and so on. And we'll see lots of these ideas, these alternating sequences, and they typically have this factor minus 1 to the n or minus 1 to the n plus 1 in them. Many sequences cannot be explicitly described by a simple formula, but they can be written down using a recursive formula. And one typical example of that is the famous Fibonacci numbers I mentioned before, 1, 1, 2, 3, 5, 8, and so on. And once we get past the first two numbers, each number is the sum of the two before it. So I can write that down using a recursive expression, that is one which just relates each number in the sequence with the ones before it. So I can write this down as a sub n is a sub n minus 1 plus a sub n minus 2. That simply says in basic English, I tell you the first two terms, a0 and a1 is 1, and then to get any further term in the sequence, you just take the ones before it, the two before it, and add them up. Now, in fact, there is a nice formula for the Fibonacci numbers. Well, it depends what you mean by nice. It's got lots of root 5s in it. You might like to Google Fibonacci numbers, and you'll see the formula for the general Fibonacci number. It's nice that there is one. Strangely and amazingly, it involves the number root 5. It's a complicated looking formula. However, there is, for example, no simple formula for the numbers satisfying this recurrence. This one says you start off with 1, and then to get each new term, you take the previous term, square it, and add 1. So to get a2, I take 1, I square it and add 1 gives me 2, and then 2 squared is 4 plus 1 is 5, 5 squared is 25 plus 1 is 26, and so on. And it turns out you can't write a simple formula that generates these numbers. The only way we can describe this sequence is by this recursion. And in the next video, we're going to have a look at looking at a number of these recursively defined sequences, and have a look at questions about increasing and decreasing and boundedness and so on.